Welcome back. Day 9 of Just Start Programming. All right, so I think the other day we stopped somewhere under chapter 7, separating modules into different files. So let's take a quick scan of yesterday's topic, and then we can move on to common collections. Yeah, so let's just do a quick review. All right, so separating modules into different files. Then again, we have lib.rs, which is the library or module packages, module libraries. So we can do it this way. And then what we have here is these keywords, the keywords that we have learned: mod, which is module, and then pub, pub in combination with use. Okay, just ignore the compilation error here. We're just going through the keywords for now. Use. So if we want to use a module inside another module, pub is a way to expose it as public because everything is private. So we can do something like this. Function can be exposed as public also, like this. And then you have different ways of creating modules. So the old style was to have a subdirectory and then you have mod.rs, which is still supported. But then you'll end up having multiple similar files like mod.rs, and try to imagine if you open this up in Visual Studio Code. So you would be seeing, yeah, mod.rs here and mod.rs here, which is quite confusing. But instead, you can have something like this: front of house.rs. Yeah. And now I think we can move on to common collections, which is also another interesting topic. So I haven't gone through the scope of this one. Yeah, so just like you, I'm also just starting in programming Rust in Rust language. So I will go through the topic together with you and see what we can learn all together. Yeah. So let's just keep an open mind and start to absorb what we can learn from this book. Okay, so let's start. Common collections. Rust's standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in array and tuples, I think this one we have already covered, the data that these collections point to is stored in the heap. Okay, so that's the difference. Unlike the built-in array and tuples, the data that these collections point to is stored on the heap, which means the amount of data does not need to be known at compile time. Yeah, because the heap, referring to the heap, can grow or shrink as the program runs. Each kind of collection has different capabilities and costs. and choosing an appropriate one for your current situation is a skill you'll develop over time. So in this chapter, we'll discuss three collections that are used very often in Rust programs. So we'll get to learn three types of collections. First one, which is vector, allows you to store a variable number of values next to each other. Okay. A variable number of values next to each other. So it sounded like array or tuple. A string is a collection of characters. So I think this one we have gone through the infamous string. But in this chapter, we'll talk about it in depth. Okay. A hash map allows you to associate a value with a specific key. It's a particular implementation of the more general data structure called a map. Okay. So vector, string, hash map. To learn about other kinds of collections provided by the standard library, see the documentation. See collections. Yeah, so we have vec, dq, linked list, hash map, b3 hash set, b3 set, binary heap. So there's a lot. Yeah. But for now, let's learn the basics: vector, string, and hash map. Okay, moving on. Storing lists of values with vectors. The first collection type we'll look at is vec. Okay, vec. And then here, I think this is T. T for, it could be any data type. Also known as a vector. So, okay, so this is what the vector looks like. Vec. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. Okay, so this is very important. Vectors can only store values of the same type. They are useful when you have a list of items such as the lines of text in a file or the prices of items in a shopping cart. Okay. Creating a new vector. To create a new empty vector, we call the vec_new function as shown in listing 8-1. Okay, so so v is immutable, vec of type integer I, so signed integer 32, and then you have vec_new. Okay, so maybe let's prepare our project, and then we can name this as common collections. I do this. CD browsed, CD projects, browsed, then cargo common collections. Okay, then CD common collections and code dot. Okay, let's run this one. Over, so we're good. Okay, so let's copy this one. Copy here. vec new. Okay, it's unused. Yeah. Can we print that one? Okay, I think we can do like B, and here let's do a debug dbg dbg. Yes. Hmm. Yeah, so you see V is empty. Okay. Okay, note that we added a type annotation here because we aren't inserting any values into this vector. Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We'll cover how to use generics in your own types in chapter 10. So 9, after error handling, then we can cover generics. For now, know that the vec T type provided by the standard library can hold any type. When we create a vector to hold a specific type, we can specify the type within angled brackets. So these are the angled brackets. We've told Rust that vec T in V will hold elements of I32 type. So this one. More often, you'll create a vec T with initial values and Rust will infer the type of value you want to store. So you rarely need to do this type annotation. Rust conveniently provides the vec exclamation macro, which will create a new vector that holds the values you give it. 8-2 creates a new vec I32, okay. It holds the values 1, 2, and 3. The integer type is I32 because that's default integer type. Okay, so default integer type. Yeah, so this one looks like an array, but we have a vec. So the one with exclamation is a macro. That's what they said. So it means that the debug is also a macro. Yeah, you can see here debug std macros. Yeah, here the macro works by using the debug implementation of the type. This. Okay. Yep. So it's a macro. Let's copy this one. Paste it here. Let's comment this out. Vec 1, 2, 3. 1, 2, 3. Because we're given initial I32 values, Rust can infer that the type of V is vec132, and the type annotation isn't necessary. Next, we'll look at how to modify a vector. Okay. To create a vector and then add elements to it, we can use push method as shown in listing 8-3. Okay, so in this case, yeah, we used mut. It means that V is mutable. V can change. Then we push 5, 6, 7, 8. Okay, let's try this one. Yeah, constructs a new empty vecti. So at this point, it was not added, but here in the Visual Studio Code, you can add it like this. And then we push, okay, push 5, 6, 7, 8. So what will be the order when we display this? Okay, so it follows the order when they are pushed. 5, 6, 7, 8, push. Hmm. As with any variable, if we want to be able to change its value, we need to make it mutable. Yeah, mutable. Using the mut keyword, as discussed in chapter 3, the numbers we place inside are all of type I32, and Rust infers this from the data. So we don't need this one, this annotation. Okay. So we don't need to add it actually. We can delete this. Still work. What is wrong with that? Stabilizer. Need to restart. See, it's doing something. Okay. So this one should still run. 6, 7, 8. Okay. Reading elements of vectors. There are two ways to reference a value stored in a vector, via indexing or by using get method. In the following examples, we've annotated the types of the values that are returned from these functions for extra clarity. Okay, so just for extra clarity, so the annotation is added. Shows both methods of accessing a value in a vector with indexing syntax and get method. Okay. Note a few details here. We use the index of 2 to get the third element. Okay, so yeah, 2 is here. 2, yeah, I think this one. 2, index 2. 0, so assuming it's the same as array, so 0, 1, 2. Then it should be, yeah, third element, which is 3. Third element, 0, okay. Element 1, 2, 3. But this is 2, so 0, 1, 2. Starting at 0 using ampersand and square bracket. Ampersand v square bracket. So what does it mean? Gives us a reference to the element at the index value. So ampersand is always all about reference. When we use the get method with the index passed as an argument, we get an option. Okay, so option ampersand t that we can use with match. You can do it like this, but you're getting a reference to I32. But if you use the get function, then you get a return of option. Option is inam. Option was inam. Or was it struck? I forgot. Let's see. Copy. Let's copy this. Maybe let's comment this out. Option is, yeah, option is enum, having none and some. Okay. So get, as you can see here, function get index. Index is the parameter, and then it returns option. So there's also an example here. None. Oh, you can do something like this. Some. If you use assert, okay. I think assert equal is also a macro with this exclamation mark. Get one. Some. You can straight away extract the value of option if you're not using it inside match. Okay. Okay. However, here get returns option third. So match third sum third equals print line, the third element is third. None, print line, there's no third element. Okay, so let's run this. The third element is 3, the third element is 3. Okay, because the third element is 3. Oh, I think from here. And then it prints out this part again. Let's make it more clear. 1 here. Let's make it 2. The third element is 3, the third element is 3. Okay. So third and third. Yeah, so that is possible. As this is like shadowing. I think the term here is shadowing. But if we remove let, they'll complain. Syntax error. Expected semicolon. Equal. Expected semicolon. Third is here. Returns option. Is it possible to do away with this experiment? Don't want to explicitly say that it's returning option. Okay, so this will complain. Mismatch types. Because third was I32 over here. All of a sudden, we changed third to receive enum option. Okay. What if we put let here? So even if you don't put in option like this, it's still fine. Okay, so that is clear. Mhm. Okay, Rust provides these two ways to reference an element, so you can choose how the program behaves when you try to use an index value outside the range of the existing elements. As an example, let's see what happens when we have a vector of 5 elements, okay? And then we try to access an element at index 100 with each technique as shown. Okay, so let's copy this. And comment this out. So here does not exist, okay? So we're accessing 100. Obviously, you only have how many elements? 5 elements. And let's run. So you get a panic. Index out of bounds. Len is 5, but the index is 100. So at compile time, it doesn't know what it knows, right? It knows. But this is placed inside the heap. So this one would be legal because we only have 5 items. Okay. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. And we run the first code. The method will cause a program to panic. Okay. Let's isolate the first one first. Then run it. Okay. So there's some stack trace here. Stack backtrace. Yeah. Prefix with underscore. Does not exist. The error is here. Okay, so it points here. Yeah, so it only executed this part because we commented this out. Terminated with exit code 101. Okay. So when you want your program to crash, if there's an attempt, you use square brackets. Okay. When the get method is passed in the index that is outside the vector, it returns none without panicking. Okay, let's see. Let's comment this out. Then I'll comment this. And then do a print line. I'm okay. Yeah, so it's still executing I'm okay. did not panic. Okay. You would use this method if accessing an element beyond the range of vector may happen occasionally under normal circumstances. Your code will then have a logic to handle having either some element or none, as discussed in chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number, it's too large and the program gets a non-value, you could tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be more user-friendly than crashing program due to a typo. Ah, very good. Now the program has a valid reference. The borrow checker enforces the ownership. Okay, enforces the ownership and borrowing rules covered in chapter 4. To ensure this reference and any other reference to the contents of the vector remain valid. So automatically it ensures that you are borrowing so that you can still use the vector variable. Recall the rule that states you can't have mutable and immutable references in the same scope. That rule applies in listing 8-6, where we hold an immutable reference to the first element in a vector, okay, mutable here, and try to add an element to the end. Okay, so this is the first. Okay, taking, but okay, this one is 1, but V we are pushing to 6. What is wrong here? You can't have mutable and immutable references. Okay, because this is mutable reference, but this one is immutable. So I think this one is not allowed. Okay. Attempting to add an element to a vector while holding a reference to an item. Okay, so we're attempting to add here, but there's an immutable variable pointing to a reference. So this is not allowed. Okay. Immutable borrow occurs here. Yeah. Code in 8-6. 8-6, yeah. Was saying that this one looks like it will work, but it won't. Why should a reference to the first element care about changes at the end of the vector? This error is due to the way vectors work because vectors put the values next to each other in memory. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements to the new space. If there isn't enough room to put all the elements next to each other, the vector is currently stored. In that case, the reference to the first element would be pointing to the allocated memory. The borrowing rules prevent programs from ending up in that situation. So that's the reason. Okay, so let's try to digest what was said here in the text. Okay, let's see. Adding a new element onto the end of the vector might require allocating new memory. Okay, so push, yeah, because we're adding to the end. So you need to find a space where you can store 6. So allocating new memory and copying the old element. Oh, okay. And copying the old elements into the new space. Okay, so my understanding is that by allocating new memory, it means there's another block. When you add this, there's another block of memory containing 1, 2, 3, 4, 5, 6, or it points to, first it points to the first memory location of the first element, and then copying the old elements into the new space. Okay, so it copies it to the new space. If there isn't enough room to put all the elements next to each other where the vector is currently stored, again, uh, vectors put the values next to each other in the memory. Adding a new element onto the end of the vector might require allocating a new memory and copying the old elements to the new space. If there isn't enough room to put all the elements next to each other where the vector is currently, okay. So the behavior would be, it will allocate a new memory and copying old elements to the new space only if, yeah, there should be only if there isn't enough room to put all the elements next to each other where the vector is currently stored. In that case, the reference to the first element would be pointing to the allocated memory. Okay. Uh, this is difficult to visualize, but somehow, let's take some example here. Where was it? Variables and mutability. Or understanding ownership. Yeah. I think there's a very good illustration here. So if we try to imagine this is a vector, and then you have element 0, 1, 2, 3. So it says that a vector requires that the elements would be next to each other. And if it so happens that in the heap, this part here is occupied and you wanted to add another element, what it will do is it will allocate another memory point to that location where it should have enough space, and then it will copy everything over to the new one, and then this part here is freed up. That's how I would imagine it, basing on that statement. Okay. The reference to the first element would be pointing to the allocated memory. Okay. Yeah. So here it will be pointing to a deallocated memory. So it's no longer valid. The borrowing rules prevent program from ending up in that situation. But that also means if it's possible that you can insert at the end with this push, where the vector will not create or allocate another memory somewhere else to make everything fit, then we can assume that this one is still pointing to the first element of the vector. I think that possibility is there. I think that possibility is there. But to be safe, let's assume that you don't have that possibility. So it's safer not to allow. I think that's the stand of the, or that's the behavior of the Rust compiler here. For more on the implementation details of vectee, see Rustonomicon. It's Rustonomicon. Example implementing vec. Where is this? Oh, there's another set of book. Introduction. What is this? Rustonomicon. This book is The Dark Arts of Unsafe Rust. Ah, that's why they came up with this name, Rustonomicon, Necronomicon. I think it sounds like Necronomicon. Oh, I remember that movie. I like that movie. It's one of those good B movies. Army of Darkness. Darkness. Yeah. Army of Darkness. Bruce Campbell. Yeah. So there was a book, Necronomicon. Book of the Dead. I think it's the Book of the Dead. Dark Arts. So I think they got the reference from that one, or I'm not sure. Okay, so let's close this book. Let's visit this book in some other time. Just keep in mind that something is there, just in case you want to dabble in the dark arts. Okay. Iterating over the values in a vector. To access each element in a vector in turn, we would iterate through all of the elements rather than use indices to access one at a time. Okay, so you can make use of for loop. Yeah, for in reference to v, then print I. Okay, let's copy this. Or let's type it in so that we can practice. Yeah, it's a good time to practice for loop. So for can I use val in referencing v, instead of print I'll use debug val. Let's run 1 2 3 4 5. Yes, that worked. So what else? We can also iterate over mutable references to each element in a mutable vector in order to make changes to all elements. For the loop in listing 8-8. Okay, so v is mutable for I in at mutable v. This one, what is this? Asterisk I plus equal 50. What does it do? What does it do? Copy. Let's copy this. Does it do? Can we do a debug here? Debug to see what's going on. No. Mm, 82,107. Okay, so it added 50 to I. 50, 82, 107. But why do we have asterisk here? What does asterisk mean? Mutably dereferences the value. Mutably dereferences the value. What will happen if we remove asterisk? Okay, so it complains. Oh, cannot use plus equal on type at mod integer. Oh, okay, okay. Because it's a mod integer here, but I did not add this in. That's the original one. In at mod, in at mod, in at mod. So if I remove this, it will still complain. Found the keyword mod. Nope. Can I remove this? Okay, so it suggests to consider making this binding mutable. Because we're changing the value. And if we remove mod, of course, it's immutable, so that is not allowed. Okay, so that's how it should be done. So if you want vec variable, the v variable to be, we can change the item. So first we need to put not here, and then in v, we are referencing it, but we put mat like this. And here we need to do something more by putting in asterisk. So dereferencing mat. I think this part is confusing. So we are saying that we have, okay, so in this case, because we are referencing v, we are borrowing v, but we're not changing v. So that's why we have ampersand. But since we want v to be changeable, we can change the value, so we put mat. So mat is together with this. Here, we can just simply display the value. But since we need to change it, I, so this is I plus I plus 50. And this one, D references the value. D references the value. Does it mean it's removing the pointer to the previous one? Because we are moving along the element. Yeah, so I think it's pointing to 100, change whatever that's in 100 plus 50. And then for us to move into 32, we need to dereference. Yeah, I think that's how it behaves, or it's just my assumption. Let's see if we have some explanation over here. Yeah, to change the value that the mutable references to, we have to use dereference operator to get to the value in I. To get to the value in I, before we can use the classical operator. We'll talk more about the dereference operator in following the pointer to the value, which is in chapter 15. Okay, so let's just accept this for now. That's the convention. Anyway, we'll get to that in chapter 15. Iterating over a vector whether immutably or mutably is safe because the borrow checkers rules if we attempt because of the borrow checkers rules. If we attempted to insert or remove items in the for loop, we would get a compiler error similar to the one we got in the code listing 8-6. The reference to the vector that the for loop holds prevents simultaneous modification of the whole vector. Okay, so in 8-6, so it avoids simultaneous change to the value of the vector. Yeah. So that's the safety that the Rust compiler can provide us the checks. Using an enum to store multiple types. Vectors can only store values that are of the same type. Yeah, this we already know. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. Yeah, variants of enum are defined under the same enum type. So we need one type to represent elements of different types. We need one type to represent elements of different types. We can define and use an enum. Okay. See, for example, say we want to get values from a row in a spreadsheet in which some of the columns in the row contains integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different value types. And all the enum variants will be considered the same type, or that of the enum. Okay, so you can define an enum whose variants will hold different value types. And all the enum variants will be considered the same type. Okay, so I think it's another grouping Then we can create a vector to hold that enum. I think that's the outer enum. And so ultimately hold different times. We've demonstrated this in listing 8-9. Okay, so we're talking about spreadsheet. So here we have an enum of a spreadsheet cell. And then cell can have int, float, and text. Okay, so in this case, the cell can have different types. Yeah. Let row vec. Okay. So by passing this enum here, then your vector can have different types. Yes. All right. Otherwise, if you just pass in int and then the next one is text, the next one is float, then it's not allowed. Okay, let's try that one. E here. Let's put the debug macro here. Then let's print row. No, ampersand. Reference to row. What's wrong? Oh, spreadsheet cell doesn't implement debug. Okay. So what you can do is, what is that? Like this. This. Debug. Yes. Is that correct? Derive. Oh, wrong. Derive debug. Derive debug. Yeah, we can see row is of type int, of type text, of type float. Okay, but say we remove this, remove this, remove this. Yeah, definitely it will not allow. Cannot find function, tuple struct or tuple variant. But can we use tuple? Oh, tuple. For tuple, then you only have one tuple element. Tuple wouldn't work. So we have proven that we cannot have different data types within a vector. But we can do some workaround by creating an enum with different data types. Okay. Rust needs to know what types will be in the vector at compile time so it knows exactly how much memory on the heap because it goes into the heap. Vector is quite complicated because when you add it to the vector, it needs to append it to the next item. If not, it will allocate a new memory and copy everything over. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled, as discussed in Chapter 6. If you don't know the exhaustive set of types a program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trait object. Oh, okay. So we have encountered trait so many times in the previous chapters. Oh, but then that will be covered in chapter 18. Okay, so we need to wait a bit. We'll get there. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vectype by standard library. For example, in addition to push, a pop method removes and returns the last element. Oh, okay. Pop. Where's it? Dropping a vector drops its elements. Like any other struct, a vector is freed when it goes out of scope. Yes. Of course, V will be deallocated outside of the scope. When the vector gets dropped, all of its contents are also dropped, meaning the integers it holds will be cleaned up. The borrow checker ensures that any references to contents of a vector are only used while the vector itself is valid. Let's move on to the next collection type, string. So does it mean that to improve performance, I think within the scope, we should have only a few things to deallocate. Otherwise, it will take some time for it to deallocate anything within scope. It's just a theory. Maybe someday we can prove that, or maybe it's written somewhere as a best practice how to improve the speed of Rust. Someday, yeah. Okay, let's move on to the next collection type, string. Okay, string. Storing UTF-8 encoded text with strings. But we'll look at them in more depth now. Now, rustaceans commonly get stuck on strings for a combination of three reasons. Rust's proper propensity of exposing possible errors. Strings being more complicated data structure than many programmers give them credit. And UTF-8, okay. These factors combine in a way that can seem difficult when you're coming from other programming languages. Yeah, but if you want to, I think if you want to learn a new programming language, then you just follow the rules. Follow the rules. Yeah. Don't insist on anything that is coming from other programming languages. So since it's our first time in learning this, then why not? Let's just accept. We discuss strings in the context of collections because strings are implemented as a collection of bytes, plus some methods to provide useful functionality. Those bytes are interpreted as text. In this section, we'll talk about the operations on string. Okay. That every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which a string is different from other collections, namely how indexing into a string is complicated by the differences between how people and computers interpret string data. What is a string? First, define what we mean by the term string. Rust has only one string type in the core language, which is the string slice str. Okay, that is usually seen in borrowed from ampersand str in chapter 4. We talked about string slices, yes, which are a reference to some UTF-8 encoded string data stored elsewhere. String literals, for example, are stored in the program's binary and are therefore string slices. The string type, which is provided by Rust, okay, string type is provided by Rust standard library. So it's different from the string literal str usually seen. Mm. Is a growable mutable own UTF-8 encoded string type. Okay, so string type is included in Rust standard library. It is growable mutable own UTF-8 encoded string type. When rotations refer to strings in Rust, they might be referring to string type, the capital S, string type, or the string slice, ampersand str types, not just one of those types. Although this section is largely about string type, which is part of the Rust standard library. Both types are heavily in Rust's standard library, and both string and string sizes are UTF-8 encoding. Many of the same operations available with vector are available with string as well, because string is actually implemented as a wrapper around a vector of bytes with some extra guarantees, restrictions, and capabilities. Hmm. An example of a function that works the same way with vector and string is the new function to create an instance. Oh, so that's why for string we also have the new function. This line creates a new empty string called s, which is mutable. Often we'll have some initial data with which we want to start a string. For that we use the toString method, which is available on any type that implements display. Okay, display trait as a string. Okay, now trait is mentioned here, display trait as a string literals do. Shows two examples. Data, okay, so this is string literal. Data to string returns creates new empty string. Okay. Yes. This method also works on literal directly. Oh, you can do something like this. To string and s. But what is s? S is literal string or string type? Let's try this out. Copy here. It's string type. You can see from here. Yeah, string type. String type. But this is string literal. From string literal, we can convert it into a string type. Okay. To string. Okay. The code creates string containing initial contents. Can also use the function string from. I think this is what what we had in the previous chapter. String from initial contents. String from a string literal. Yeah, so either string literal with a toString or string type using from, then you input the string literal. Okay. Because strings are used for so many things, you can use many different generic APIs for strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string, string from, and toString do the same thing. So which one you choose is a matter of style and readability. Remember that strings are UTF-8 encoded, so we can include any properly encoded data in them, as shown in listing 8-14. Oh, nice. Nice. What is this? Hello. Oh, I think everything here is hello. Hola. Okay, let's copy this. This is interesting. Yeah. Yeah, of course. The variable name itself is hello. I wonder how to type this in. This one is konnichiwa. This one is, I don't know. I don't know Korean. This one is ni hao, hola, hola or hola. Okay. Uh, all of these are valid string values. Okay. A string can grow in size and its contents can change, just like the contents of vector. If you push more data into it, in addition, you can conveniently use plus operator or the format. Okay, so there's another macro here, format macro, to concatenate string. So plus you can use to concatenate or you append it to another string. Appending to a string with push str and push. Okay, so okay, we can grow a string by using the push str. So push str is part of string type. So append. Okay. After these two lines, S will contain foobar. Foo push to this one becomes foobar. Okay, push str method takes a string slice because we don't necessarily want to take ownership of the parameter. For example, in the code listing 8-16, we want to be able to use S2 after appending its content to S1. Okay, let's analyze. S1 is mutable of string type containing foo, then S2 equals bar. Okay, S1 push str, that is valid because it's mutable. Then we are pushing S2. S2. Okay, so now this will be deallocated S1 on a full bar. S2 is S2. Happened. S2 is S2. I thought we are pushing it to S1. We want to be able to use S2. Okay. For example, in the code listing 8-16, this is the one. We want to be able to use S2 after appending its contents to S1. Okay. The push str method takes a string slice. Okay, so it takes a string slice because we don't necessarily want to take ownership of the parameter. So push str doesn't want to take ownership of S2. So it takes a string slice. So that's why S2 here is still valid. Okay, so that's the behavior of push str. Okay. If the push str method took ownership of S2, we wouldn't be able to, yeah, correct. If so, if we don't know how push str works, then yeah, my assumption would be S2 would be invalid, which is this one. We wouldn't be able to print its value on the last line. However, this code works as we'd expect. The push method takes a single character as a parameter and adds it to the string. Okay, push. Okay, so push underscore str, string literal. That's why I think that's the naming convention, str. But here, push takes in a character. As a result, S will contain lol. Yeah, S will contain lol. Okay, so I can do that. Push str plus sign or push for characters. Concatenation with the plus operator or the format macro. Oh, okay. Format macro. Often you want to combine two existing strings. One way to do so is to use the plus operator as shown in listing 8-18. Yeah, so here string hello, hello world, yes. S1, S2, then S1 plus ampersand S2. Note S1 has been moved here and can no longer be used. Ah, okay. Because S1 is moved here. Okay. Yeah, but the value of S1 is inside this. And then we are referencing S2. So S2 is not moved, so meaning S2 can still be used. And then we have S3. Now S3, only S3 and S2 can be used. Let's check if our analysis is correct. Let's put it here. And so if we debug, debug this, and I'll put S1. Of course, it will complain. But if you put S2, should be fine. Yeah. But if you use S2 the second time, of course, it will complain. Here, you can use S3. Yeah. So I think by now we have already mastered ownership. Okay, the string S3 will contain hello world. The reason S1 no longer valid after the addition and the reason we use reference to S2 has to do with the signature of the method that's called when the plus operator uses the add method whose signature looks something like this. Okay. Plus operator uses add, but how did it become plus here and you have function add? So self S, which is a reference to the string literal. In the standard library, you'll see add defined using generics. Okay, now it mentions generics. Okay, so maybe that's how you can have plus sign, have function add here, generics, and associated types. Here we have substituted in concrete types, which is what happens when we call this method. String values. Okay, we'll discuss generics in chapter 10. Chapter 10. Okay, that's after error handling. This signature gives us the clue we need to in order to understand tricky bits of the plus operator. So there are those possibilities. First, S2 has an ampersand, meaning that we're adding a reference. Okay, I think we did this analysis. This is because the S parameter in the add function, yeah, here, only add ampersand str to a string. We can't add two string values together. But wait, the type of ampersand S2 is ampersand string and not ampersand str. Yeah, that's correct. That's correct. Yeah, because this is a string. But why does it work? Specify in the second parameter to add. Why does listing 8-18 compile? The reason we are able to use %s2 in the call to add is that the compiler can coerce the ampersand string argument into ampersand str. When we call the add method, Rust uses a, oh, there's another concept here, deref coercion, deref coercion, which here turns ampersand s2 into ampersand s2 string slice. Okay, I think this is the slice, string slice. We'll discuss deref coercion in more depth in chapter 15. Oh, it's getting complicated. Smart pointers. Okay. Okay. Reference D. Reference. Okay. Okay. We'll get there. Because add does not take ownership of the S parameter, S2 will still be valid. Yeah. I think somehow we were able to interpret it together, other than this part which we missed. So apparently there's this dereference coercion. Deref coercion. Okay. Second, we see in the signature that add takes ownership of self because self does not have an ampersand. This means S1 missing S-18 will be moved. Yeah, okay. So by parameter, that one is self. Looks like we'll copy both strings and create a new one. This statement actually takes ownership of S1, prends a copy to the contents of S2, and then returns ownership of the result. In other words, it looks like it's making a lot of copies, but it isn't. The implementation is more efficient than copying. If we need to concatenate multiple strings, the behavior of the plus operator gets unwieldy. Ah, yes. Plus dash plus this. So now if the assumption is this one, okay, ideally this one will have a reference here. At this point, S will be tic-tac-toe with all of the, okay. Difficult to see what's going on. For combining strings in more complicated ways, we can instead use format macro. Okay. You can just simply do format. This code also sets S to tic-tac-toe format. Macro works like println, but instead printing the output to the screen, it returns a string. Ah, okay, so it returns a string. Which makes me think, I think format for date or date and time, I think can be used. The version of the code using format is much easier to read, and the code generated by format macro uses references so that this call doesn't take ownership of any of its parameters. Okay, from now on we will use format if we want to concatenate. Let's not use this one. I think this is not a best practice. Format it is. So let's copy this. It's here. To 8. S2, S3. Oh, we did not print S. Print line S. So, yeah, of course, it would. Oh, oh, what did I do? Ah, tic-tac-toe. Tic-tac-toe. Yes. Okay. Indexing into strings. Okay, many other programming languages accessing individual character in a string by referencing them by index is valid and common operation. However, if you try to access parts of a string using index syntax in Rust, you get an error. Consider the invalid code. Okay, hi. And then, yeah, element 0, it looks like takes letter H. Yeah, that's assuming I know Rust, but actually I don't know Rust. So this one will have an error. Okay. String indices are ranges of U size. U size, okay. Can use chars, and or bytes. Oh, so it will show you these are the alternatives. Okay. The error and the note tell the story. Yeah, here tells the story. Rust strings don't support indexing. But why not? To answer that question, you need to discuss how Rust stores strings in memory. Very important point. Internal representation. A string is a wrapper over vec. Okay, let's look at some properly coded UTF string. Hola. Okay, so if we try to imagine this is vec unsigned 8-bit. Okay, so it's UTF-8. In this case, len will be 4. 1, 2, 3, 4, which means the vector storing the string hola is 4 bytes long. Each of these letters takes 1 byte when encoded in UTF-8. The following line, however, may surprise you. Note that the string begins with a capital Cyrillic. I hope I pronounce it correctly. Z, not the number 3. Oh, where is it? Is it this one? Okay. If you were asked how long the string is, you might say 12. Well, yeah. Visually, oops. Chapter, chapter. Where were we? UTF-8. Oh no. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. Visually, yes. But in fact, Rust's answer is 24, and that's number of bytes it takes to encode this in UTF-8, because each Unicode scalar value in that string takes 2 bytes. Okay. Therefore, an index to string bytes will not always correlate to a valid Unicode. Unicode scalar value. To demonstrate, consider the invalid Rust code at hello 0. Okay, because now this is was saying it's 2 bytes. You already know that answer will not be 3. First letter encoded, first byte. Okay, so it says it will be 0, but will it at least show the byte equivalent? Maybe not. Maybe the compiler will stop us. Yeah, 208 second is 151. So it would seem that answer should in fact be 208. But 208 is not a valid character on its own. Returning 208 is likely not what the user would want if they ask for the first letter of the string. However, that's the only data that Rust has byte index 0. Yeah, it's 208. Users generally don't want the byte value returned, even if the string contains only Latin characters. Hi, we're valid code and return the byte value. We return 104, not H. The answer then is to avoid returning an unexpected value causing bugs that might be discovered immediately. Rust doesn't compile this code at all and prevents misunderstandings early in the development process. Yeah, so it's not allowed. Can't do that. With the possibility that it could be Unicode character. Bytes and scalar values and this is grapheme clusters. Oh my, I heard this. Another point about UTF-8 is that there are actually 3 relevant ways to look at strings from Rust's perspective as bytes, scalar values, and grapheme clusters. Okay, what are grapheme clusters? The closest thing to what we would call letters. Ah, okay. If we look at the Hindi word, this one, written in Anagari, sorry for mispronouncing it. I don't know how to pronounce this. It is stored as a vector of U8 values that looks like this. Okay. That's 18 bytes and how computers ultimately store this data. If we look at them as Unicode scalar values, which are what Rust's card type is, those bytes would look like this. There are 6 car values here, but the 4th and 6th are not letters. 1, 2, 3, 4, 5, 6. Okay, so this and this. They're distinct diacritics that don't make sense on their own. Finally, if you look at them as grapheme clusters, you'd get what a person would call 4 letters that make up Hindi word. Ah, okay. Oh, there's something here like a tail. So I think this is part. This one doesn't have a tail. And this one would have like an antenna. Yeah, antenna. What is antenna? Singular. Antenna singular. Antenna singular antenna. Antennas. Antenna. Antenna is singular. So we're correct. Rust provides different ways of interpreting the raw string data that computers store so that each program can choose an interpretation it needs, no matter what given language the data is in. The final reason Rust doesn't allow us to index into a string to get a character is that indexing operations are expected to always take constant time. Constant time 01. But it isn't possible to guarantee that performance with a string, because Rust would have to walk through the contents from the beginning to the index to determine how many valid characters are there. Slice strings. Slicing strings. Indexing into string is often a bad idea because it's not clear what the return type of the string indexing operation should be: a byte value, a character, a grapheme cluster, or a string slice. If you need to use indices to create string slices, therefore Rust asks you to be more specific. Okay. Uh, so hello means string slices. Here S will be percent str contains 4 bytes. Okay, so it will be 4 bytes of the string. Earlier we mentioned that each of these characters was 2 bytes, which means S will be 3A. Oh, so that will be confusing because 3A would be 4 bytes. Yeah. Okay, so this one is always bytes. If we were to try to slice only part of the character's bytes, it's something like this. Okay, so I think this one is not allowed. But panic at runtime the same way as if an invalid index were accessed in a vector. Ah, okay. Okay, that is clear. You should use caution when creating string slices with ranges, because doing so can crash your program. Methods for iterating over strings. Best way to operate on pieces of strings is to be explicit about whether you want characters or bytes. For individual Unicode scalar values, use chars. Okay. Calling chars on separates out and returns two values of type char. You can iterate over the result to access each element. And it will display two values. Alternatively, the bytes method returns each raw byte, which might be appropriate for your domain. Okay, so like this. Raw bytes, if it's bytes. Cars will be car. Okay. Be sure to remember that valid Unicode scalar values may be made up of more than one byte. Getting grapheme clusters from strings, as with this script, is complex, so functionality is not provided by standard library. Crates are available on crates.io if this is the functionality. Okay, so strings are not so simple. To summarize, strings are complicated. Different programming languages make different choices about how to represent this complexity to the programmer. Rust has chosen to make the correct handle of string data the default behavior for all Rust programs, which means programmers have to put more thought into handling UTF-8 data upfront. This trade-off exposes more of the complexity of strings than is apparent in other programming languages, but it prevents you from having to handle errors involving non-ASCII characters later in your development cycle. The good news is that standard library offers a lot of functionality built off the string and str types to help handle these complex situations correctly. Be sure to check out the documentation for useful methods like contains, for searching in string and replace, for substituting parts of a string with another string. Let's switch to something a bit less complex. Hash map. Okay, hash map. How long is this? I think we can see. We can read through. I think this would be easy to understand. I hope. It was saying it's less complex. Let me take a quick break, maybe 2 minutes, just to grab some water. All right, I'm back. Let's continue. Storing keys with associated values in hash maps. Okay, so the last of our common collections is the hash map. The type hash map K and V stores a mapping of keys of type K and values of type V using a hashing function, which determines how it places these keys and values into memory. Many programming languages support this kind of data structure, but they often use different names such as hash, map, object, hash table, dictionary, or associative array, just to name a few. Okay, but in Rust, it's hash map. Hash maps are useful when you want to look up data not by using an index, as you can with vectors, but by using a key that can be of any type. For example, in a game, you could keep track of each team's score in a hash map in which each key is a team's name and the values are each team's score. Given a team name, you can retrieve its score. Okay. We'll go over the basic API of hash maps in this section, but many more goodies are hiding in the functions defined on hash map. Okay. By the standard library. As always, check the standard library documentation for more information. Creating a new hash map. One way to create an empty hash map is to use new. Oh, just like in string or vector. And add elements with insert. Okay, scores, insert, string. Okay. We're keeping track of the scores of two teams whose names are blue and yellow. The blue team starts with, okay, blue starts with 10, yellow's team starts with 50. Okay, so in this case, you are inserting, pushing. Okay, insert. Note that we need to first use the hash map from the collections portion of standard library. Of our three common collections. Oh, so we didn't use for string and what was that? String and vectors. But for hash map, we need to do something like this. It's not included in the features brought into scope automatically in the prelude. So now it has something to do with the prelude. Although they all belong under standard library, in this case, it seems it's not automatically brought into scope. Okay, prelude to remember. Hash maps also have less support from the standard library. There's no built-in macro to construct them. For example, just like vectors, hash maps store their data on the heap, just like vectors. The hash map has keys of type string and value of type A32. This hash map. Yeah, okay, this one. Like vectors, hash maps are homogeneous. All of the keys must have the same type and all of the values must have the same type. Okay, so if it's string here, it will be string all throughout. Integer all throughout. I think this can be enum. Yeah, this can be enum, definitely. To give it more flexibility. That's what we learned from vector. Okay. Like vectors as okay. Accessing values in a hash map. We can get a value out of the hash map by providing its key to the get method as shown in listing 8-21. Okay, so we have this team name. Oh, okay. So we're just segregating it like this, team, and putting it here. Oh, okay, because this is insert and here get team name. Okay, so we are referencing copied unwrap 0 score. Oh, this is complex. Let's see what happens here. Here score will have the value that's associated with blue team, and the result will be 10. Okay, first line. Second line will be, okay, the get method returns option. No, it's referring to this one. Option, okay, this one will return option reference to vector. If there's no value, or for that key in the hash map, get will return none. Okay, so it's, if you don't have value blue, then it will return none. This program handles the option by calling copied to get an option I32 rather than option at a reference to I32. Okay, by calling copied to an option I32. Because of this. Okay, it copies the return value. Okay, I32, which is 10. Then unwrap or the to set score to 0 if scores doesn't have an entry for key. This one is strange. What if it's none? Then would copy still work? We can iterate over each key value pair in a hash map in a similar manner as we do with vectors using for loop. Unwrap, then unwrap or to set score to 0 if score. Okay. Unwrap or. So if it doesn't have, okay, so at this point it's none copied. If it doesn't have any value, then it becomes 0. Yeah, so that's interesting. So somehow there's some form of error handling here. Go. I think that will be the next topic. We can iterate over each key value pair in a hash map in a similar manner as we do with vectors or using a for loop. Here, okay. So this one looks like a tuple scores. Yeah, but I can do something like this. Okay. This code will print each pair in arbitrary order. Okay, so it doesn't mean it's always blue and yellow. It could be yellow now, blue later, blue now, yellow later, perhaps. And we are referencing scores. Okay, hash maps and ownership. For types that implement copy trait, like I32, the values are copied into the hash map for own values like string. The values will be moved and the hash map will be the owner of, okay. So values will be moved and the hash map will be the owner. Okay. String, field, hash map new, so field name, field value, insert. Field name and field value are invalid at this point. Try using them and see what compiler error you get. Yeah, so for those who are watching, let me copy this and put it here. Mhm. Value already moved. Value moved here. So that won't be allowed. But we can display and time. Ah, no. Let's use debug instead. Favorite color, blue. Favorite color, blue. Okay, so favorite color is the key here. Then blue is the value. Key value. Oh, this one looks like JSON. Okay. Field name. Not insert. If we insert references to values into the hash map, the values won't be moved into the hash map. The values that the references point must be valid for at least as long as the hash map is valid. Okay, so there will be lifetimes. The values won't be moved. Okay, the values won't be moved to the hash map. Ah, if we insert the references. Okay, okay, understand. So uh, here instead of map, if I put in first a field name, of course this will complain. But if we insert ampersand field name, that should be fine. Yeah? Because we are inserting references. Field name equals favorite color. Hmm. The values that the references point to must be valid for at least as long as the hash map is valid. Okay. Validating references with lifetimes. That will be chapter 10. Generic types, traits, and lifetimes. Okay. Updating hash map. Although the number of key and value pair is global, each unique key can only have one value associated with it at a time, but not vice versa. For example, both blue team and yellow team could have the value 10 stored in the scores hash map. Okay, each unique key can only have one value. Okay, understood. Could have the value 10 stored in the scores hash map. When you want to change the data in the hash map, you have to decide how to handle the case when a key already has a value assigned. You could replace the old value with a new value, completely disregarding the old value. You could keep the old value and ignore the new value, only adding the new value if the key doesn't already have a value. Or you could combine the old value and the new value. Okay. To overwrite a value, we insert a key. Okay, insert a key and value into hash map, then insert the same key. Okay. Oh, so same key, new value. The hash map will only contain one key value pair because we're inserting the value for the blue team's key both times. Code will print blue 25. Okay. blue 25. The original value of 10 has been overwritten. Okay. Adding a key and value only if a key isn't present. It's common to check whether a particular key already exists. The key doesn't exist in the hash map, the existing value should remain the way it is. The key doesn't exist, insert it and your value for it. Hash map have a special API for this called entry that takes the key you want to check as a parameter. The return value of the entry method. Okay, so entry is another keyword. Entry method is an enum called entry. Okay, enum entry that represents a value that might or might not exist. Let's say we want to check whether the key for the yellow team has value associated with it. If it doesn't, we want to insert a value 50. And the same for the blue team using entry API. Code looks like this one. Let's see, insert blue 10. Scores entry, using entry. Yellow or insert 50. Let's say we want to check whether the key for yellow team has a value associated with it. If there's a value associated with it, insert 50. Okay. Yellow or insert 50. Blue or insert 50. If it doesn't, we want to insert the value 50 and the same. Okay. If it doesn't have a value, how do we read this again? Let's say we want to check whether the key for the value yellow team has a value. Okay, if key has value, if key doesn't have value, okay, maybe that's how we read this. If key doesn't have value, insert 50. Key doesn't have value, insert 50. So I think this one is still 10. Here. Or insert method on entry is defined to return a mutable reference to the value for the corresponding entry. Mutable. Okay. Mutable reference. If that key exists, and if not, it inserts the parameter as a new value for this key and returns a mutable reference to the new value. Okay, so it will return a reference to the new mutable reference to the new value. This technique is much cleaner than writing logic ourselves, and in addition, plays more nicely with the borrow checker. Okay. We can do it the hard way, or we can just make use of this as a best practice. Or insert. Okay. Running the code in listing 8-24, maybe we can run it from here. Yellow 50, blue 10. Yeah, yellow, because yellow didn't exist. Doesn't exist, insert 50. Blue exists, so will not be inserting 50. I will use 10. So it has a built-in checking, error handling all in one. And also borrow checker. It plays nicely with borrow checker. Okay. Now, if we want to update a value based on the old value, another common use case of hash map is to look up a key. Okay, we're looking up a key and then update it based on the old value. For instance, 8-25 shows a code that counts how many times each word appears in some text. What does it do? Hello world, wonderful world. Hash map new. Okay, for word for word in text that's split. Okay, text. Okay, then split white space. So I assume it's splitting the white spaces. Iterating through each 1, 2, 3, 4 word hello. Okay, then you have a map entry word is hello. Okay, word is hello. Entry, okay, if there's hello in the map, we don't have it yet. So insert hello with 0. Count colon. Count. Where's count? Ah, here, count. Count. Okay, so there's no first value is 0. Count plus to count plus 1. So it will increment. Hello would be 1. Yes, that's correct. Then world 2 wonderful. No. Hello wonderful world. Hello. You might see same key value person. Yeah, so it could be in different order. Yeah, doesn't have to be hello world wonderful. Okay, but here world, I think world will be overwritten. Yeah, because eventually you'll have the same key. So then in the, just like in vector, we can update the value using, okay, this is math, so we need to dereference so that we can still update count. Yeah, dereference count. Hash functions. By default, hashmap uses a hash function called zip hash. It can provide resistance to denial of service attacks involving hash tables. This is not the fastest hashing algorithm available, but the trade-off for better security that comes with the drop in performance is worth it. Okay, so a compromise between performance and security. If you profile your code and find that default hash function is too slow for your purposes, you can switch to another function by specifying a different hasher. A hasher is a type that implements build hasher trait. Okay. So if you don't want zip hash, then you can this is build hasher. You can do build hasher. So I think that's the purpose of generic types, traits, and lifetimes, chapter 10. You don't necessarily have to implement your own hasher from scratch. Creates.io has libraries shared by other Rust users that provide hashers implementing many common hashing algorithms. Okay, so finally we are at the end. We are at the end of common collections. Vector strings and hash maps provide a large amount of functionality necessary in programs when you need to store, access, and modify data. Here are some exercises you should now be equipped to solve. Okay, given a list of integers, use vector and return the median. In sorted, the value in the middle position and mode, the value that occurs most often. Oh, I think this is some exercises. Convert string to pig Latin. Okay, using hashmap vectors create a text interface to allow a user to add employee names. Add Sally to engineering. Oh, okay. The standard library API documentation describes methods that vector strings and hash maps have that will be helpful for these exercises. So we need to look into the API documentation. We're getting into more complex programs in which operation can fail. It's a perfect time to discuss error handling. We'll do that next. Okay, all this implementation, I think I'll save it for another day so that we can move on to other exciting topics. I think the basic understanding on how vector strings and hash maps works, I think that's already clear for everyone who is watching this video. Yeah, if not, maybe you can post some comments, and then I could revisit this topic, and we can do this together also and see our confidence level in programming in Rust. Okay, so thank you for watching. Thank you for keeping me company. It's good to have a programming buddy to go through learning a new programming language. And yeah, so hopefully you'll stay with me all throughout the final project. Yeah, and hopefully we'll have the confidence that yeah, we can develop anything in Rust together. Because just like you, I am also a beginner to Rust programming language. All right, so I'll see you in the next day for error handling. Thank you so much.